Let's look at the graphs of some incredibly important functions. We're going to call them library functions or parent functions. And we're going to use these as building blocks to create lots of other more complicated functions. Our most simple function would just be a constant. We've seen these. Their graphs are horizontal lines. And they're pretty boring, but of course they're a good building block for more complicated stuff. So constant functions, horizontal lines, pretty simple. Another one would be incredibly simple in terms of what it does as a machine. It just takes a certain input and spits out the same output. So for example, if the input is 2, the output is 2. So 2, 2 is on the graph. Pretty darn simple. And so far, we're not in anything new at all. It's just straight lines, but we're emphasizing the idea that it's a function. So more generally, we could have a straight line like 2x minus 1. We know what that's going to look like. We know a lot about this kind of thing. It has a constant slope of 2. It's got a y-intercept of minus 1. It's not too hard to see the x-intercept is 1/2. Lots of good stuff. Okay, so I'm gonna assume that straight line functions are mostly a place of confidence for us. So what about stuff that gets more interesting? Well, we've seen this one a little bit. It kind of cropped up in a few problems, but let's focus on the absolute value function. Okay, so that's a very interesting, or it's a very easy thing to picture and just say, oh, it looks like a v. Let's see why that's a v. If I put in input 1, I get output 1. Okay, if I put input 2, I get output 2, because the absolute value for a positive number doesn't do anything. If I put input minus 1, well, what's the absolute value of minus 1? I get 1. Okay, not too surprising. If I put in input minus 2, absolute value of minus 2 is plus 2. Notice it's got to be something where the graph is always above the x-axis, because the output values, the y values, always have to be positive. Now, one mistake people make here is undercomplicating this. Once you see like, oh, absolute value of x, v, I'll just remember that. It's so easy. And it's tempting to think it's this one thing that all hangs together. In some ways that's true, but it's really, really helpful to say to yourself, we often want to think of the absolute value function as two half lines rather awkwardly put together. Remember when we do like absolute value equations and inequalities, it very often splits up into this and this, or this or this, kind of two pieces that are kind of a pain to deal with. That's telling us that a lot of the time this is really not so fun. It's incredibly important. It's really meaningful. It's like talking about distance and size and magnitude, but a lot of the times it's more complicated than you might think. And the notation looks just like streamlined parentheses. That is incredibly dangerous. It's really doing something pretty drastic to a number by half the time doing one thing and half the time doing something else. What about something that is really nice? Let's say, where am I? L maybe? X squared. Ooh, how about an equal sign? Oh my gosh, that is so nice. Okay, let me delete these guys. Okay, this is so good. This is quadratic algebra, and this is going to be our absolute favorite curve, maybe besides a circle. This is a parabola. It is the simplest expression for a parabola. That is the name of that very particular kind of curve. You're going to see a lot of other graphs that look vaguely like this that you'll be tempted to call a parabola. Only this kind, and we'll talk about exactly what is a parabola and what's not this year, and even we'll come back to it next year in a little more generality. Okay, let's see why it has this shape. Well, if the input is 0, what's 0 squared? It's 0. Aha. If the input is 1, what's 1 squared? Oh, it's 1. Okay, so far so good. Similarly, minus 1 squared is 1. Okay. Notice that when I square, kind of like with absolute value, but here it's much more elegant, the minus sign goes away, and so I get the same answer whether or not x is negative or positive. What's 2 squared? That's 4. Aha, it's doing it right. Hey, the computer actually is getting the right answers. Amazing. What's minus 2 squared? Minus 2 squared is 4. Aha, okay. Let's just do a little bit further. What's 3 squared? It's 9. Notice that it's getting steeper as it goes out. That's why it's curved, right? It's not like the straight line. 0 and 1 didn't go to 2, 3, 4, 5. It went 0, 1, 4, 9, and then it would go to 16. It's going to get steeper and steeper. Let's zoom out a bit. And we see it gets steeper and steeper as you go out. Okay, so you get this nice, pleasing curve that has a lot of great properties. And that is the graph of y equals x squared. Okay. What about y equals x cubed? Let me actually reverse it a little bit, and let's plot the points first, actually. Okay. So let's plot, well, 0, 0 for sure. 0 cubed is 0. 1 cubed is 1. Oh, wait, I need to delete the parabola too. Okay. What if I did 2 cubed? 2 cubed is 8. Ooh, it's kind of similar, but it's going faster. It's getting big faster. 3 cubed is 27. Whoa, I'm already going to have to zoom out a bit to even see that. Whoa, okay. It's getting steep real quick. Okay. So that tells us, let me just plot, let me kind of cheat a little bit. I'm going to put in a little requirement. It's only going to plot this curly brace. Notice it's kind of like set builder notation. It's not quite, but it's how you can tell Desmos to only plot part of something. I'm asking it to just plot the positive part, the part of the y equals x cubed graph for positive x's. It kind of looks like a parabola, but let's contrast it. Okay, it really does go up quite a bit steeper. Okay, so it's more aggressive, and in the inside, it's actually more aggressive at getting flat. Notice the quadratic, you could have said it does two things. It gets flat near 0 and steep away from 0. The cube graph does both jobs better. It's going through 0, 0, and 1, 1, so it has those exactly in common with squaring, but it gets steeper faster and it gets flat faster, or better, more aggressively when you go towards 0. So higher power kind of does the same job better. Now, we've already seen a lot of times that odd powers for negatives are very qualitatively different from even powers. So what's minus 1 cubed? It's minus 1. What's minus 2 cubed? Okay, so this is very different from squaring. There, whether or not we put a minus or a plus in, we got plus. Here, these guys are going down. That's very, very different. Okay, let's zoom out and see the last one. Yeah. Okay, and so let me just kill this restriction here. Aha. So now it's quite different. The y equals x squared graph, that parabola, is symmetric across the y-axis, a reflection symmetry. And the cube graph, let me take away the x squared graph. The cube graph has a different kind of symmetry. If you take this and you rotate it 180 degrees, boom, boom, boom. If you rotate it 180 degrees around the origin, you'll get the same thing. So this guy is symmetric under rotation by 180 degrees around the origin. We'll talk about other ways of thinking about that symmetry, because that's really, really helpful. Okay, let's do one more that introduces some a bit of weirdness. So far, I haven't done anything dangerous, but we know we have two famously dangerous operations. Let me just focus on one of them to not make the video super long. Let's do 1 over x. Okay. Let's clear the clutter here. Okay, so these were the old ones. Let's look at 1 over x here. That's kind of funky. This guy, let's check what's going on with this one. So 1, 1. 2, what's 1 over 2? It's 1/2. Okay, looks like it's good. Oops, that's not good. 3, 1/3. Okay, cool. Sorry, getting confused about the parentheses here. How about minus 1? Well, 1 over minus 1 is minus 1. Okay. Yeah, looking good. So again, it has that rotational symmetry. So like minus 2 minus 1/2. If you look at it, that 2, if you rotate it around, boom, oops, I shouldn't have clicked. That one, boom, let's try it, minus 3 minus 1/3. Aha, okay. So that's cool. But what's really weirder about this one, but which we shouldn't be surprised by, is that it's got really weird behavior. I'll put bad question mark. Most of the times we consider this bad, but not always. Near x equals 0. Okay, and that's because if I take like 1/10, what's 1 over 1/10 or 1 over 0.1? It's 10. I get a very big, or a relatively big number. Okay, and that's only going to get more extreme if I take like 1/100th as my x value. That wouldn't have been weird at all for squaring and cubing. I just get a nice small number. But 1 over 1/100th gives me 100. These values are blowing up. I have to zoom way out to even get that on the graph. Okay, they're blowing up. And if I just get closer and closer to 0, let's see. Well, yeah, let's see. What is that? That's 1 over 100,000. Wow, I'm going to zoom way the heck out there. Oh my God. Oh, there it is. Okay. So simply by putting in inputs that are relatively close to 0, these outputs just blow the heck up. And so we see that from the actual graph that it becomes super, super steep and blows up. We say that blows up to infinity. Okay. So this is pretty weird, but that's where I'll end this video. So we say, we're going to say this a little more officially with some terminology in a minute, but we just say informally that 1 over x blows up. I'm going to put in quotes to infinity because it's not actually ever giving a value infinity. Infinity is not a number that we do algebra with. As x gets nearer and nearer to 0. Okay, so it's a great building block, but it's a building block for more kind of funky behavior that we get from fractions, and we've known that for a long time. We know that 1 over 0 is the most famously dangerous thing in math, and even when you get close to 1 over 0, you got to watch out.